Welcome back. Discussion 18. Problem 72 on page 329. Okay, so we're given a situation where a bullet is being fired. We'll call this a bullet. Is being fired at a pendulum bob that's just hanging. We're going to need a little more room. So here's this thing, it's hanging, and this bullet is going to strike this. Right? It's going to come over and whack this thing. So this is scenario 1. Scenario 2 is this has been struck. Okay, so we're given that this thing has V0, it's going to strike this block, can then continue on through, and this thing now has some momentum. Immediately after the collision, it's just going to be in the x-hat direction, right? So we can have, so now we have m, we'll call this m block, V0 is equal to 1/3 mass of the block, V0, because that's what we're given here, plus, sorry, this is the bullet, mass of the bullet, that's what B is for. So, and then now is the mass of the block times velocity. So we want to know, what is this? No problem, let's figure it out. mb V0 minus 1/3 mb V0. Right. So now we've got, this is equal to 2/3 mass of the bullet V0, and then we're going to divide out this mass. So now we have the velocity of the pendulum is given as follows. There we go. Okay, so that's just using conservation of momentum, right? Now, we want to take this same scenario, because ultimately we are asked to find an expression for the speed of the bullet before the collision. So we want an expression for V0. We could write it in terms of V, but we don't know what V is, right? So let's keep going and figure out what we can do. So, okay, so now the bullet is way over here, and it's got, you know, some speed. But we don't actually really even need to care about that at this point, because now that the pendulum is in motion, we can just use the energy of the pendulum. So this has some kinetic energy here. It was transferred from the bullet hitting the pendulum, right? It's gonna go up, and we want to know, so this thing is able to swing all the way around. So we could take this and let's set it up here. So in order to determine this, we can use conservation of energy, and we can use it just so that this thing is barely making it around. So what I mean is the pendulum swings up and then just barely has enough to go all the way around. That is in fact what we're told in the problem. So what that means is we have a potential energy and we have a kinetic energy where this velocity goes to 0. So we just are going to use, we are just going to equate 1/2 mv squared. This is the initial energy, right? There's no potential here. Is equal to 1/2 mv, this goes to 0 squared, plus mgh, right? So this goes away, and now we're just left with 1/2 mv squared. This is equal to mgh. Mass cancels out, right? So now we have v squared is equal to 2gh. So what is h? We don't want to just leave it in terms of something that we don't understand. So we're told at the beginning of the problem, so we write this down, that this pendulum length is L, and so if this thing goes all the way up here, so if this thing travels all the way up here, it has gone a distance of 1 to L. So that's what h is. So then we're going to write h as 2L. So that means that v is equal to 4GL square root of, which means that it's equal to 2 times GL square root of. So here's V. So now we have two expressions for the same velocity, right? So we have this expression for the velocity of the pendulum, and we have this expression for the velocity of the pendulum. Let's set them equal to each other and see what we can find out. So let's say V is equal to 2 times square root of GL is equal to 2/3 mass of the block over mass of the pendulum times V naught. Now what is it we're being asked? We want to know an expression for V naught, the initial speed of the bullet, right? In terms of things that we can understand. So in other words, in terms of known constants. And so the masses of the objects in the system are going to be known, and the length of the pendulum can be known. So let's just solve for V naught. So the 2's cancel, and we're going to have square root of GL times M bullet. Excuse me, I keep saying block. What I mean is bullets. This is M of the bullet. This is meant pendulum, so I'll call that P, just to make it clear of what's going on. So this is bullet, this is pendulum, okay? And times 3. So that's the answer. Okay, so problem 74, we're given a setup where there's a famous experiment and they're shooting alpha particles at a sheet of metal, right? And so this metal atom is going to have a lot more mass than the alpha particle. That's the basic idea. So what we're asked to find in this scenario is, what is the velocity? What's this? Actually, I think it's what's the speed of the massive particle after the collision, or what's the speed of the alpha particle after it collides with the nucleus, right? That's what we're asked to find. Okay, so then we can use this. In the chapter summary, we're told that this is an elastic head-on collision. And that's exactly what this is for, a one-dimensional elastic collision. So what I've written down here is pretty much exactly what you'll see in the book. And then the initial speed of particle 2, or the massive particle, is 0, right? So that's going to go away. So then what we end up with, also, before I do that, recall that we're told in the problem the nucleus is much more massive than the alpha particle. So what that's suggesting to us is that we can approximate a little bit here. So since this is way more massive than like this term here, where you have m1 minus m2 is roughly negative m2, and then what we have here as well, m1 plus m2 is also roughly m2. So what does that suggest to us? Well, to me, that suggests that V1 final, the alpha particle's velocity final, is going to be negative. Like, these are going to cancel, right? So this is, okay, so let's just do this. Negative m2 over m2, right? Because we approximated them to be much larger than m1, so those don't really have much of effect, and so that's the negative of the initial velocity, right? Because that goes away. So V1 final is equal to negative V1 initial. That's what we just found. Now, what does that insinuate about the massive particle then? Well, if we plug in for this is another equation that's in the back of the book, or in the summary of chapter 11. So here again, initial velocity of the massive particle is 0, so this term goes away. And now we're left with this term here. And so if we're holding this assumption that the particle is much more massive than the alpha particle, if particle 2 is much more massive than the alpha particle, then that suggests here that this is just going to be m2, 2m1 over m2, right? But if m2 is way, way greater than m1, then this is going to be on order of 0, right? Because this is huge, and this is not so huge. This just goes to 0. That's what we're being told. So that means that V2 final is on order of 0. Okay. One thing that we should note before moving on is that mass of gold is around 10 to the negative 25 kilograms, and the alpha particle is around 10 to the negative 27 kilograms. So if we look at this here, we have roughly 10 to the negative 27 over, we'll call this 10 to the negative 25, right? So then the relationship between these, the final velocity is going to be 10 to the negative 2. So a very small number, 10 to the negative 2 times the initial velocity. Sorry, that's what I meant to say. So the final the final velocity of particle 2 would be on order of 10 to the negative 2 times the initial velocity. If we're using standard gold. Okay, so the next problem, number 75. Going back just a little bit, if we actually plug in, if we want to find the speed of the nucleus after the collision, right? So then we take this, we're given the value, this is kilograms, this is the alpha particle. Then we're told that we have to, what is it, 6.7, we have to add these up, 20 kilograms, and gold here, 25 kilograms. Okay, and then the speed that we're given is 2e to the 7 meters per second. So if we plug all of this in, remember that from this equation, this thing is equal to 0. So that doesn't do anything for us. So if we plug all of this into this equation, which can be found in the back of the chapter, then we end up with a value of, gives us a value of around 8.03 times 10 to the 5 meters per second. And I would say that's not 0. If you take the ratio of the two, right? So this is 2 orders of magnitude, and that's actually what I had estimated here, right? 2 orders of magnitude lower than the speed with which you start. So yeah, I mean, it's going to be the same. So if you take 8.03 times 10 to the 5 over 2 times 10 to the 7, and this is meters per second over meters per second, then you're going to end up with a ratio of about 10 to the negative 2, close to 10 to the negative 2. Right? So that is what we estimated. But is it reasonable to approximate this as being 0? I don't think so. So let's move on to number 75. Okay, so we're told that the alpha particle flies at the nucleus and then is deflected, it tells you 90 degrees. So the alpha particle actually travels at 90 degrees in an opposite direction, right? So what does that mean? It means that it's going to go up after the collision. The particle is going to go up this way, and then this thing is going to have some velocity going in that direction, right? Or we say it's this way, probably. So, well, anyway, we can't actually use the same equation that we did for the last problem because it's not a one-dimensional head-on collision. It's no longer a one-dimensional head-on collision. So what we can use is conservation of momentum. So let's talk about the x direction. Initially, in the x direction, we have mass of the alpha particle times the speed of the alpha particle. And then we're going to have no motion in the x direction for the alpha particle. Remember, it's changed course by 90 degrees, but we are going to have some motion of the nucleus, and we don't know what the angle is, so we can try to figure that out. right? So that's the x direction. Now the y direction, we had 0 initial velocity in the y direction for the alpha particle, right? But then we're told that it changes course by 90 degrees, and we have an alpha mass and a velocity. Oh, we're told it's the same velocity. We'll just call this alpha. We're told that it's the same speed. Okay? So I'm imagining that this thing is going to go the opposite direction. If this slams in here and goes up, then this is going to come down in by some angle, right? So that's going to be m of the nucleus times the speed times sine of the angle. So we can use this to solve for the angle. So I'm just going to use this equation here and solve. Okay, so now we have two unknowns in one equation. Well, let's just use the other one then. So that means that m alpha, so first I use this here, and now I'm using this one here. Okay, so now this, oops, no, that's right. M plus is equal to v plus sine of the angle, right? So now look, we have, this is the same as this, so we can set those equal to each other, and then we get something that's pretty apparent. These cancel. This is going to be 1 is equal to tangent theta. Well, I mean, you either know this, I mean, you could plug it into the calculator. What you're going to get is theta is equal to 45 degrees. So that's your angle. So then, okay, well, now that we know that, we can plug it back into this equation and figure out what is the speed. Okay, so let's do that. M plus, and this is going to be equal to, so I'm just using the x equation from before, right? The x momentum equation from before to solve for the speed. So cosine of 45 degrees is square root of 2 over 2. That's 1 over square root of 2. So then we take square root of 2 times 6.7 e to the negative 27, 2e to the 7. This is going to be over 3.27, I think. Yep, 27 e to the negative 25. And that will give you the speed of the particle. So let's figure it out. This gives you a value of 5.79 times 10 to the 5 meters per second. In fact, that's very similar to what we had found before for the other problem, where it was, what was the value? It was 8 times 10 to the 5, right? And now we're at 5 times 10 to the 5. So it's a little bit less, but some of that momentum was transferred to change direction for the first particle, right? So, okay, next problem. We're given a wheel that's programmed to follow a specific cycle. It accelerates from rest and reaches an angular speed that you're given here. I'm going to write all this down in a second. I'm just reading the problem. So we have a wheel that accelerates. So there's a wheel, and it accelerates from rest, and it gets up to a certain speed. And then it just kind of runs for a few seconds, and then it decelerates, right? And then so that's going to slow it down, and it goes to a stop. So what is that going to look like graphically? So let's see, what do we have? We have a speed, and we have time. So for 3.4 seconds, this thing gets up to an ideal speed of 25 revolutions per second. We'll call this W1. So here we get up, over this time we get up to the speed. We know what this is. This is 25 revolutions per second. Okay, and then for 3 seconds, this thing runs. So what's this, 6.4 seconds, right? Because this is a 3-second interval. at 25 revolutions per second, and then over a course of 15 seconds, so a much longer period, this thing slows down like that and goes to 0, right? So we could do a couple of different things to solve this, and in fact we will do a couple of different things to solve this, because just doing this way, what I'm going to do next is not enough. That's not good enough for this discussion. So I'm going to show you 2 ways to find it. So, all right, so let's use kinematics first, actually. Let's do that first, and then I'll go to this graphic, because the graphing one is actually way easier, and you could use it if, let's say, you're on a timed exam. It might make your life really easy. But let's do kinematics, which, by the way, also makes your life really easy if you know how to use it. So on page 338 in the textbook, at least in my textbook, this is what we have. We have a bunch of kinematic equations that we can use to solve. So the first one that I'm going to use is the second equation on the page, and it shows you this. Right? And we have, these are all directly analogous to the non-rotational kinematic equations. So if we have delta theta, that's actually what we're being asked to find. What is the angular displacement? Right? And then so this is going to be 1/2. Initial was 0. We got up over the course of 3.4 seconds is what we're given. We got up to 25 revolutions per second in 3.4 seconds, right? So this is going to give us 25 times 3.4 over 2. That's going to be revolutions. And we can figure out, if we have a revolution, we can figure out what is the angle, like how many radians did we pass through. I think we're actually just asked to find the number of revolutions total. Yeah. Okay, so this actually gives us a value of 42.5 revolutions in the first phase. Okay? So then next, we can use the equation that we're very familiar with. Theta naught plus omega times t plus 1/2 alpha t squared. Okay, so for this period, we're told that it stays constant at a constant angular speed for 3 seconds. Well, what that means is that there's no acceleration. So this will be kind of convenient that we can just get rid of this acceleration term here. We can also just say that delta theta is equal to omega times t, right? And so that's 25 revolutions per second times 3 seconds. That gives you 75 revolutions. So that's the second phase, all right? Next. Okay, and next for the last phase, I mean, we can use the same equation that we did before, because what we have here is delta theta is equal to 1/2 omega naught minus omega times, what was it, 15 seconds, that's what it was. This is actually plus, but it doesn't really matter because the final, so the initial, okay, here's what we'll do, 1/2, the initial speed that we're given is 25 revolutions per second. Remember, we're in the third phase, right? So we start out in this part of the curve, we start out here at 25 revolutions per second. And then we go for 15 seconds, and the final velocity is 0. So what does that give us? That gives us 25 revolutions per second times 15 seconds. That's going to equal 187.5 revolutions. So if we add, let's just do this. Yeah, if we add the sum of each angular displacement, we have 187 plus 75 plus, what was it, 42.5. And that's going to equal 305 revolutions total. Okay, the other way to do this is to just sum up the area. If you can draw out a curve like this, I mean, it was a pretty straightforward setup, so if you could draw out a curve like this, you could just take the area, right? So this would be the area of 25 times 3.4 divided by 2, which is pretty much what we just did, right? And this is 3 seconds times 25 seconds. So I'm just showing you the area, right? 25, 3, right? And then this was what? 25 by 15 divided by 2. So this is, you have to split this in two, right, from basic geometry. So then we go here. So what was it? It was 25 times 3.4 divided by 2 plus 3 times 25 plus 15 times 25 divided by 2. And in fact, if we just look at what we did, that's exactly what we have for each one. 25 by 15 over 2. 25 times 3. 25 by 3.4 over 2. So we did exactly that same thing, but we used kinematic equations instead of looking at it graphically. So either one of those methods works. All right, so the next problem, we're given a merry-go-round, and we're told that 2 children are on the merry-go-round. Right? Let's go here, make some room. This is number 36 on page 356. All right, so we're given the information that they both weigh the same. M1 is equal to M2 is equal to 25 kilograms. Okay, they weigh exactly the same. Now, we have a child that is 0.75 meters away from the center, and then we have another one that is 3 meters away from the center, right at the edge, pretty much. That's what we're told. Obviously, this is not to scale. This is less than 1 meter. This is 3 meters, okay? So here we have this thing is spinning counterclockwise. We're given that information. And we're told that it spins at a constant speed. So there is no angular acceleration. Okay, part A asks, what is the angular speed of each child? Well, we're given a relationship for angular speed, and that is linear speed divided by the radius. So the linear speed in this case is the translational speed. We're told that this thing has a translational speed of 12.5 meters per second, and that's what we're told the child at the edge is moving with, right? So this translational speed here is 12.5 meters per second. So for child 2, we have 12.5 divided by the radius, which is 3 meters, and that gives you 4.16 radians per second. So one thing that we can note about the relationship between two items on a disk that are spinning is that no matter where they are, their rotational speed is going to be the same. But this translational speed is going to be way less. So this speed, if we're saying that this is M1, I'm just putting this here to show you. If this is M1, this translational speed is going to be much less than the translational speed on the outside. So anything on here is going to be moving faster translationally. So this would be like 12.5 meters per second. This would probably be way less, like, I don't know, 2 meters per second or something. But the rotational speed will be the same. They're going, because this thing, if we draw a line here, which we have, this whole line is going to be moving at the same rotational speed. So that means that this is the same for the other child as well, which is 4.16 radians per second. Next, we are asked to find what angular distance does each child move in 5 seconds. So we need to use kinematic equations for that. So we want to know what is the angular displacement. We're given a speed. We're told that there is no acceleration, right? We were given that information in the problem statement. So the angular acceleration goes away. We're given now, this is going to be delta theta, excuse me, delta theta is equal to rotational speed times time, which is going to be, time is 5 seconds, rotational speed is 4.16 radians per second, times, what was it? I just said it, 5 seconds. That gives us a value of 20.8 radians total. So they both traverse 20.8 radians. Again, that does not mean that they have both traveled the same amount of distance linearly, because that's going to be a little different. All right, next, part C. What distance in meters does each child move in 5 seconds? Okay, there we go, because I was just talking about this. So, okay, so now we have the angular distance, right? This is the total angular distance traversed by both children, okay? And if we recall basic geometry, well, that's not a circle. If we recall basic geometry, we have some relationship here, right? Where this is going to be an arc, and this arc is equal to r theta. This is r, this is theta. This arc here is s equals r theta. So now we can just apply this to both children. So let's say r1 theta. So theta is the same for both children. The radius for each child, however, is not the same. By the way, r, when I say radius, I'm implying the distance from the center for each child, right? Not the total radius of the merry-go-round. This is 3 meters would be the total radius of the merry-go-round, but this guy is sitting at 0.75 meters, so that's important. So, okay, so child 1, 0.75 meters times 20.8 radians. That equals 15.6 meters. That's the, what do we call it? That's the linear distance that this child has moved. And then the next one is going to be 3 meters times 20.8 radians. And so that means we have gone, this child number 2 has traveled 62.4 meters. So see, that's what I was saying before. So this guy, child 1, has traveled way less linearly than child 2. So because this one is closer to the center, they are going way less distance overall. Still traveling the same number of radians, same number of angular distance, but different in linear distance. So that's pretty interesting. Okay, part D. What is the centripetal force experienced by each child as he or she holds on? Which child has a more difficult time holding on? Okay, so here we have to set up a force equation. So let's look at what centripetal force is. So we have centripetal force is going to equal, well, we know it's mv squared over r. We could probably use that. But even easier is if we take this, remember that relationship we had earlier where omega is equal to v over r, so that means that v is equal to r omega, right? So let's use that. So r squared omega squared over r is equal to m r omega squared. So that's an equation that we can use to find the centripetal force for each child. So let's go with this. Centripetal force 1 is equal to the mass, 25 kilograms. It's the same for both children. The radius is 0.75 for the first one. And then the angular speed is also the same. Radians per second, and this is squared. Okay, so that gives us a value of 324.48 newtons for the first child. That's the centripetal force on the first child, who is closer to the center. Okay, child 2, 25 kilograms times 3 meters times 4.16 radians per second, all squared. That's going to give us a value of 1,297.92 newtons. And this is the child that's on the edge, so this is quite a bit more, right? It's almost 3 times as much. Almost 4 times as much, excuse me. So that's pretty interesting. So the child that experiences the greatest centripetal force is the child that's out on the edge. And so this child way over here, as they're traveling around here, they're going to have to hold on way tighter than this child in here. In fact, the closer you get to the center, the smaller your centripetal force is going to be, and eventually you can just stand kind of in the middle and hang out. So that's the answer. Thanks.